questions for today? Number 28. All right. Number 28. What is the change in volume? So I know immediately that I need V2. That result is 60 milliliters, so that 60 must go up here. 60 milliliters of gas is cooled from 2. Now when it says from 2, 2 means 2 conditions. So I'm going from 33.0 degrees C plus 273 to 5.00 degrees C plus 273 equals. Now, to avoid some confusion on significant figures, although this isn't perfectly correct, what we're going to do is we're going to just add the two numbers together, and then when we get finished with the problem with its temperatures, we're just going to go back to the original problem, look at the numbers that are in the original problem, and that will be the number of significant figures that we'll have in our answer. Okay? So we're not going to worry about, we're adding 33.0 to 273, and we've got to round off the nearest whole number. We're not going to worry about that. We're just going to add the two numbers together, put the number down in our calculation. Then when we finish, we're going back and look at our original numbers, which will be those, the ones that were in the problem. Okay, so I don't need pressure, so I'm going to cancel pressure out, cancel it out over here, and I'm looking for V2. So V2 is equal to V1 T2 divided by T1. Plug in chunky numbers. V1 is 60, and I think it's 60.0, wasn't it? So I didn't write it up there. Milliliters. T2 is going to be 278 K, and T1 is going to be 603, correct? 306. All right, so my T1 is going on the bottom, so it is 278 K. My T2 is going on the top, 306 K. And our answer then is going to be slightly larger than 60. Probably going to be around 70. Just as an estimation. Now, estimation is a good thing on these problems because it's so easy to put numbers in wrong. If you notice that 300 divided by 278 is going to be a little less than 1. Or a little more than 1, excuse me, a little more than 1. So that means this number is going to be bigger than 60, but not by a whole lot. Okay? So my answer should be what? All right, 66.0. Is that rounded correctly? Milliliters. And we go back to our original problem, and we see three significant figures, and that's how many I want in. What? I put it in wrong. Thank you.
I was wondering.
Yeah, y'all keep me straight. By this time of the afternoon, I get kind of brain dead. So T2 is supposed to be 278K up here and 306K down here. So my number is going to be less than 60 by probably about the same amount as that it was more than 60 there. Yep, 54.5. Okay, so it's about the same amount left as it was more. Well, okay. That's the sort of error that you can make as well. So pay attention. Do better than I did. Y'all are smarter than me. Y'all can do that. Thank you. Andrew, for correcting.
Email to my
Thank you. Like I said, it's been a long day. It has been Monday all day. Do what? On this thing. Yeah. Well, on any of the ones that have temperatures. Because all of them, any of the others you do, you're going to get your number from your problem anyway. So we're just going to use the numbers in the problem. That's what you can do on any of these types of problems. You're not doing anything to multiply times some weird number. All right. Any other questions from the homework? 40 what? 46. Question 46. All right. What is the pressure? What is the temperature? So T2 is what I'm looking for. I'm sorry. My bad. Wrong one. What is the pressure? So P2 is what I'm looking for. So the at tells me that my T condition, T2 condition, is going to be standard. Now, you can either write 0 degrees C plus 273, or we already know that 0 plus 273 is 273, so you can save yourself a bit of writing there by just writing down 273K. Or if you want to, you could say that standard temperature is 0 degrees C or 273K. So that means I could substitute either one of those in for standard temperature, since I got to add 273 anyway. All right. A gas has a pressure of 3.370 atm at 50 degrees, 50.0 degrees C plus 273 equals 323 K. Okay? Now, what don't you have anything for? Volume. So I'm going to mark out volume. Shouldn't be any different from what we've been doing, or I would not expect you to be able to do it. So you just use the same sort of pattern as we've been doing. Looking for P2, so P2 is equal to P1, T2, T1. And you plug and go. When you ask for temperature, what kind of unit do I want my temperature to report it in? Celsius. So I think we have to subtract 273. This is not one of those, but it could have been if they'd given you two pressures and asked for a temperature. Okay? So you plug and chug, get the answer. Should have 3 significant figures in your answer. Okay? Any other questions? Which one? 31? 31. 31. All right, 31. What volume? First thing I want to do is find out what I don't know, or what I'm looking for. What volume? And then I have 8.00 liters given as the other volume. What volume of this gas at? So as soon as I see the word at, I know what volume and that at go together. So minus 23.0 degrees C plus 273. That's going to give me a 250. Okay. All right. Then I back up and it says at 210 degrees C, a gas has a volume of. That's present tense. I put it in the wrong place. That's easy to rectify there. You're right, I put it in the wrong place. Keep me straight. Keep me straight. Oops. All right, so my other temperature is given as 210 degrees C plus 273. That would be 483 K. Don't have any pressure. All right. So we plug and chug. We're looking for V2. Pressure's gone. V2 is equal to V1 T2 divided by T1. Make sure you put your T2 and T1 in the right place. And you should have 8.00 liters. T1 is 483K and T2 250K. I look at that, I look at those numbers and I estimate that my answer is going to be close to 4. Because 480 is almost 500, and 250 times 2 is 500. So if I were to reduce that fraction, I would get about 1/2. So my answer should be close to 1/2 my volume. Okay? So what is my answer? 4.14 liters. Okay. All right. Any other questions? The last one. All right, we're going to start. We're going to skip Dobson's Law since we have several people who are out over the course of today. I'm going to skip that until tomorrow. The combined gas law is where we're going to number 61 through 79 even. 61 through 79 even, because 2 of the odd problems have a blank space in them. I originally assigned the odd problems, but rather than have to fool with those 2 blank ones, we just do the even. All right. Now, before we go on to work on that type of problem, I'm going to work some examples on board here in a minute. I want you to work on 39. Work on 39. And I will give you a few minutes to work that. All right, we're looking at number 39. So what does it say? It says what will be the volume. So my volume, question mark. If the temperature, the Kelvin temperature, is double. So let's say that I let the Kelvin temperature be 1. What's double 1? 2. I can put any number there I want to as long as I double the second number. That's all it says, double it. And then if I let the volume be 1, no matter what I put over here, which is V2 is equal to V1, T2, T1, everything on the right-hand side has a 1 in it right now. Or if I take and put a 1 here, let's just put a 1 there. Everything over there is what? 1. So what's the volume? 1. So my first volume that I'm thinking about is equal to 1. Now I'm going to double this number to 2. So now I have 1, and, excuse me. Go back and start over. 1, and I have a 2 for T2. I don't even have to worry about units here. You just ask if it's doubled or tripled or halved or whatever. So you look at it, and now the volume is, the second volume is 2. So what happens between the first and the second volume? It doubles. Now this is not rocket science, but you're going to see this type of question in college. College professors love it. You're going to see it on ACT and other standardized tests that you have to do to get in different schools. So I'm trying to teach you a strategy on how to do it. It is not an optional thing. You've got to learn it. You've got to figure this out if you want to be successful. All right, on the next level. I could have, like we did last time, I could have said, well, I can ignore everything except B2, T2. If I ignore everything except B2, T2, B2 is equal to T2. So I'm keeping everything else constant. The only thing that changed was T2. Now you have to be careful, because if you're looking at something like B1, P1, P2, and I'm doubling the pressure, then I'm looking at B2 is equal to 1 over P2, because it's on the bottom. I can't automatically bring it up to the top of a fraction. It's still going to be on the bottom of a fraction. So I can just compare it that way and just look at the two parts. So if you are comparing something with the denominator of a fraction, that denominator of the fraction has still got to be a denominator of the fraction. You put a 1 above it. Okay? All right. That's one I did the other day with this one. All right. So let's do on page 3 of your handout. I'm going to do number 1A and number C. The C is a little weird, and B is just like 1A. I'm not going to work both A and B. All right. Calculate the volume at. Calculate the volume at SPP. So my V2, my T2 is going to be 273K, and my P2 is going to be 101.3 kPa. I can choose any unit of pressure. But I chose kPa because the other pressure in the problem is in kPa. I want to save myself a step. Yes. I'm on page 3, number 1A, bottom of the page. Combined law. All right? You understand why I picked kPa? Save myself some work. If the volume, which is 5.05 decimeters cubed, are collected at 27.5 degrees C plus 273K and 95 kPa. That's 95.0. So this one is going to be 0.50, carry 1, 0, 3. Okay. Now, what can I mark out? Nothing. Got it all. So I got to work with it all. I'm looking for V2. What am I going to divide both sides by? P2, P1. So V2 is equal to V1, P1, T2, and divided by P2, T1. All right? Now, I've got V1 is 5.05 decimeters cubed. P1 is 95.0 kPa and 101.3 kPa. And T2 is 273K and T1 is 300.5 K. Now, a little side note here. When you are given standard conditions, when your problem says STP, your standard pressure and standard temperature are going to be on opposite sides of your division line. Pressure is not always going to be on the bottom, temperature always on the top, but they are always going to be on opposite sides when you use this equation, when you have the term STP in the problem. Okay? So you can kind of check, test check kind of thing whenever you're on the test. You don't have the answer to the question. Now, let's look at this. 95 divided by 100 is very close to, but a little greater, a little less than 1. And 273 divided by 300 is a little less than 1. So if I were to calculate and come out with an answer that's 5 or greater, it's wrong. It's going to be less than 5. Probably not much more than less than. It's going to be around 4.3. So it's going to be in that range. So 4.3 what? 0 decimeters cubed. kPa cancels. Kelvin cancels. Okay? So you see what I'm trying to do is trying to reinforce that estimation your elementary teacher taught you how to do, but you never would do. You take out the calculator so you have exactly the right answer rather than estimate. This is the reason you estimate. Because then you can check to see if you calculate right. So it's a way of a quick way of checking. All right. Now, for the next question. Any question about this one? It's like what we've been doing, except instead of having two of you mark out, the P's of the T's of the B's, you got to keep them all, and you got to calculate. So this next one is a fun problem. Assume the respiratory rate of a person is 15 breaths per minute, and one breath contains 500 centimeters cubed of air at 200 degrees C. So I have one breath at 500 centimeters cubed, and that is per breath. And I've got at 20 degrees, so 20.0 degrees C plus 273, 293, okay, plus, and 99.5 kPa. Now, the question is what volume, which I already knew that, so it didn't matter. But whenever I see the volume at those conditions, I go ahead and plug those in. I want to know the volume of the air in meters cubed corrected to standard conditions. So I'm going to need 101.3 kPa, and I'm going to need 273 K. Does an individual breathe in 1 day? So the first thing we need to do is every time my breath goes in and out, I'm breathing 500 centimeters cubed. That's a half a liter for every breath. But the temperature is 20 degrees C and 99.5 kPa. So the first thing I need to do is to adjust that volume to the new condition. So I'm going to make this a touch smaller here. All right, I'm going to come over here and adjust my formula. B2 is equal to P1, 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 T2, P2, T1. Now I want to plug and chug. I'm going to kind of move this over here. My volume is 500 centimeters cubed, and that is per breath. It's okay to write it down there. That's okay. Doesn't matter. I'm going to use that in a minute. My P1 is 99.5 kPa and 101.3 kPa. My P2 is 273K, and my P1 is 293K. So I calculate that, I'm going to get 400 something as my answer. What? Pardon? 470? 458. All right, so 458 centimeters cubed per breath. Okay. Now I'm going to see if I can move this over, and I can move it over a little bit more, because that's not what I'm asked. What am I asked? What is the volume in cubic meters and per day? I have breaths and I have centimeters cubed. That's the amount that moves in and out of my lungs at 20 degrees C and 99 kPa. Okay? So, that's every breath. I'm asked what volume of air every day. So what do I know about breath? Look at the problem. And what? I know there are 15 breaths. Per minute. Now, without picking up my calculator, do any of you know how many minutes there are in a day? I don't. If I watch Rent enough, I might not know how many seconds are in a year, but I don't know how many minutes are in a day. But what do I know about minutes that might help? That minute, I don't know how many minutes are in those hours. 60 minutes in 1 hour, and then yes, 24 hours in 1 day. Alright? So hours, minutes are gone. Now, I've got centimeters cubed per day. I want meters cubed per day. Now, I don't see anything over there that's going to help me with meters cubed. I see centimeters cubed and decimeters cubed, but they're not equal to meters at all. But your math teacher has taught you, as long as I do the same thing to both sides of an equality, it's still equal. If 12 inches equal a foot, and I multiply both sides by 2, then 2 feet is equal to 24 inches, right? As long as I do the same thing to both sides. So what I do know is 100 centimeters equal 1 meter. That is on the cheat board. And if I cube the 100 centimeters and the 1, then I'm going to get an equality. Now, get this out of the way a bit. I've got to say 100 cubed centimeters cubed is equal to 1 cubed meters cubed. Is it really necessary to say 1 cubed? What's 1 times 1 times 1? 1. But I do want you to understand that I am cubing that 1. Even though I'm going to write it down as 1. I have cubed it. If you don't know how to do 100 raised to the third power on your calculator, you can say 100 times 100 times 100. And that'll be 100 cubed. It has to be a million. But I'm going to put this in here. I've got centimeters cubed, so 100 cubed centimeters cubed is 1 meter cubed. And that's how I got it. I cubed both sides of that equality. Now, here's a hint to you. If I don't know how to use this calculator and get a cube, then I look at the first thing I would do is look at the keys on it and see if there's something raised to the x power, like y raised to the x power. That probably is going to do it for me, but I'm not sure. And this is an important test. Maybe it's the ACT. I really need to get this right, because I know how to work the problem. I don't want to get the wrong answer. What's 3 cubed without using a calculator? Not 9. 27. So I know that's right. I know 27. So I can use since I'm not sure. Alright, since I'm not sure, I can put in 3, and then I can punch that key and put in 3 again and equals, and if it equals 27, I've got the right keystroke. If I need to hit that key first, I may not get the right answer. So you see, you can use that strategy where you know what the answer is going to be. Use your calculator to figure out the keystroke for numbers you don't know. So you have really weird numbers. That's a good test-taking strategy that I used to use quite frequently when I take tests. And I wasn't sure about what number to use. I know that the log of 100 is 2. When you start learning about logs, you will know that the log of 100 is 2. So if I need to find the log of something, and I know that one, I can put it in my calculator and get my keystroke sequence, and then I can put the weird number in there and get the right answer. Because I know the answer is 1. Right? So that's just a strategy that you need to, use to improve your test-taking skills. All right, I'm through talking at you now. And